Okay, guys, so right now we're going to talk about integration by parts. So this is one of the first new, like truly new techniques you're going to learn in Calculus 2. Integration by parts is a technique that we will use to deal with the antiderivative of a product. Okay, so let's suppose we start with two functions, u of x and v of x, but for simplicity's sake, I don't want to deal with all the, the d of x and all that. So I'm just going to call it u and v. So if I ask you to find the derivative of u times v, so right here, I just have u times v, and then I ddx'd it. So I took the derivative of u times v of the product with respect to x, and I built this derivative over here, okay? So now, if I just simply rewrite it below, and I rearrange it so that the v is in front of the du dx, and the u is in front of the dv dx, that's all I did. So this is what I'm dealing with right now. Now, if I wanted to, I should be able to get back to where I started by integrating both sides, right? So now this would become u times v, right? Because the derivative and the integral are inverse operations of each other. So you're left with u times v. And then we have v times du dx, okay? But if we want, we could just write du dx, as du. So this would become u du plus the integral of u dv. Let me make sure I wrote that right. V du, I'm sorry. I wrote my lettering wrong. V du and u dv. So all I did was I took this and rewrote it as du, just for simplicity. And then I took this and rewrote it as dv. Okay, so this is what I'm left with at this point. So as far as the integral is concerned of v du, when you integrate that, v is basically not related to the du. So we're going to have this as, so if we simplify this, we're going to have v du, and we're going to get, let's see here, let's subtract this guy over to this side, because we can't do much. Oops. Hold on real quick, you guys. I think I have it written backwards in my notes. So what I'm going to do is I'm going to subtract this guy, u dv, over to here. Because you guys understand that we can't really do much with either of these because the letters don't match, right? It doesn't really work how we want. So now this cancels, and now I'm left with u dv equals negative integral u dv plus u times v equals the integral of v, I'll leave a little space here, integral of v du. So now the thing is I can now also subtract this over. Okay, so this will become 0. This will become 0. Sorry about that. So now we have negative integral of u dv is equal to negative uv plus the integral of v du. Okay. However, we don't want the negative in front, so we're going to divide. We're going to divide this by -1, by -1, by -1, or multiply by -1, whatever way you were taught. This becomes u dv. This will then become uv minus the integral of v du. Okay, so if we are able, so all this is saying is if we are able to ever rewrite an integral in this fashion, this would be what we're working with. Okay, now the thing I want you guys to note is one of the goals of integration by parts is to have the integral of v du be easier than what you started with. Okay, so one of the goals of the integration by parts is to have the new integral that's in your final or that's in your I guess your solution to be something you know how to integrate. The whole point is you don't know how to integrate what you started with, so you're trying to break it into pieces, and then the new thing that you have to integrate should be easier than what you started with. If it's not, then that's something to worry about. That's something you definitely want to think about. Okay. So I had one instructor tell me that a good way for students to memorize this is to memorize that the integral, and by the way, this is our integration by parts formula, uv minus the integral of v du. So this is, she called it, Dr. Hughes called it, she called it ultraviolet, and it seems to help a lot of students memorize it. Ultraviolet voodoo. So ultraviolet voodoo. So UV minus the integral of VDU, ultraviolet voodoo. So that's not actually a math thing. That's just some way to help you memorize it. It just makes it easier and faster for you to deal with. But I just wanted to reiterate that this is the formula we need. Okay, so I'm going to show you a technique that I use to, not me personally, everybody uses this. This is how I want you to set it up when you're taking your exam or when you're dealing with problems. But there is one little thing to memorize. This is called LIATE. And this deals with logs, inverse trig, polynomials, exponentials, and then we have trig, regular old trig. Okay, so this is kind of how you decide what's going to be u and what's going to be dv. So that's kind of your big thing, is you have to find u and you have to find dv and declare them. So you start up here with logs. Logs should always start off as your u, and then you kind of work your way down. And then the very bottom, dv, should be your priority for trig, and you work your way up. And it basically helps you decide what should be your u and what should be your dv. Okay, so if you see log of something or natural log of something, you should probably name that u, and then the other thing, the other function that's in there, a dv. The reason for that is sometimes I would say for a lot of logarithmic and inverse trig, finding the derivative of it is going to be easier than integrating it. And you'll see what I mean in a second. So let's take a look at an example problem. Pretty much a very straightforward, kind of almost like one of the iconic problems of integration by parts, like one of the, I guess the main reasons you learn it is to deal with problems like this. So we have a polynomial x times a trig function cosine of 3x dx. So our u sub won't work. And then if you try to do u sub and then switch around the variables a little bit differently, it still won't work. So what we're going to try is we're going to try integration by parts. So in order to do integration by parts, we have to name a few things. We have to name u, but if we name u, that means we need a du. And then we have to name dv, but if we have a dv, then that means we have to find v. So according to LIATE, log should be my u. Well, I don't have any logs. Oh, but it does say trig should instantly be my dv. So what I'm going to do is I'm going to say cosine of 3x is my dv, okay? I guess cosine of x dx, okay? And then my u will be plain old x, right? Because we don't have any logs, so I'm here, we don't have any logs, we don't have any inverse trig, we do have a polynomial, so that could be u or dv. In this case, we already had a choice for dv, so we're going to choose polynomials to be u, and then we know du is going to be dx, okay? So the only thing we're missing is v, so you have to do a little bit of work. So let's integrate this. So if I integrate this problem right here, right, I should get a little u sub on that. My u would be 3x, and my du would be 3 dx. Now remember, maybe I shouldn't even use u, maybe I should use like m. So m would equal 3x, so dm would equal 3 dx, right? Divide both sides by 3. So we're going to end up with a 1/3 sine of 3x. You guys see why I didn't want to use u again? Because if I use u again, then we're dealing with u's and dv's and du's, and then it's going to get confusing. But in reality, it's two different problems. You're doing this little problem over here, like on the side, like you're doing the integral. Oops, I'm sorry. You're doing this problem over here on the side where you would be doing the integral, like it was some separate problem. And then you could do u equals and du and so on like that, okay? But, you know, it's whatever is easier for you as long as you show me some work. Okay, so now we've declared officially what u is, what du is, what v is, and what dv is. So that means we can now rewrite this problem. So we're going to rewrite this problem as u dv, right? U dv. We said dv was cosine 3x dx, so this would be u dv. Okay. So that means that we have u times v minus, u times v minus the integral of ultraviolet voodoo, v du, voodoo, right? So now I'm going to substitute in what I know. I know that u is worth x. I know that v is worth 1/3 sine 3x, right? Minus the integral of v, 1/3 sine of 3x times, it says ultraviolet voodoo, du, but du in this case is just dx. So you guys see that from right here, this gave me this, right? So hopefully you're seeing what I'm doing here. This 1/3 sine is my v du. So literally what you do is once you have this form, you just go back and look at the problem and plug in what you said u was, what you said v was, and what you said du was, and that'll take care of everything, okay? So now, let's see. This now becomes x over 3 sine 3x. Now, what's the integral of 1/3 sine 3x? Well, we know that's going to be the same u sub up here, the same u sub we did here, but now it's with sine. So we're going to get minus, and then we're going to get 1/9 cosine 3x plus c. Now, there's a little catch. Because this time right over here, I am integrating this integral of 1. Let's put the 1/3 out front. Of 1/3 sine 3x. We're going to have another u. So I'm going to get another 1/3. So that's why that will become 1/9 integral of sine u du. However, we know the integral of sine is negative cosine. Now here's the catch, or not a catch, but you see this negative? Well, there's already a negative here. So I have to make that plus now, okay? So then, let's just write, I basically have the answer, but I'm just gonna write it cleaner. X over 3 sine 3x plus 1/9 cosine 3x plus c. I guess I don't need these parentheses. And that would be your final answer. Okay, I mean, I could have left it here as well, you guys, but I just wanted to write it with the plus sign in the middle. So if you make a little mistake in anything up here, your whole problem is going to be wrong, right? So no matter what you do, if you mess up your u and your v and your dv, it's just going to go south from there. So you really got to be careful when you declare this. So you should always have this little box right here. This box is required for all of your integration by parts. You have to show me what you're naming, okay? So let's take a look at another one. Let's see what else we got. Okay, so let's look at the integral of x squared e to the 2x dx. So what I'd like you guys to do is to pause the video and try to determine what's your u and what's your dv. Okay, remember you have to name that. So you have to go u equals du, you know, v equals and dv. So the two things you have to declare are these two guys right here. And then the other two you find. So take a minute, pause the video, declare that, and let's see where you're at. Okay, so hopefully you guys, what does LIATE say? Okay, so LIATE says, let's go back up here. LIATE says logs first. Well, we don't have any logs. Then it says inverse trig for u. We don't have any inverse trig. Then it says that polynomials could be in the middle. It could be u or it could be dv, but we do have an exponential, right? E to the 2x. So according to this, the exponential is closer for dv. So then what we should do is we should name our exponential dv. So our exponential is e to the 2x dx, right? And then our u is x squared, okay? So then we know that the derivative of x squared is 2x dx, oops. And we know our integral of e to the u, or I'm sorry, e to the 2x is going to end up being 1/2 e to the 2x, right? And you don't have to put the plus c up here because it'll come up through in the rest of the problem anyway. So we have our dv is e to the 2x, so then our v is going to be 1/2 e to the 2x. So we have everything we need. So we're going to say the integral of u dv is going to equal u times v, so this would be x squared times 1/2 e to the 2x minus the integral of v du. So v is 1/2 e to the 2x and du is 2x dx. Okay, so let's rewrite this a little bit. I guess I could have wrote that better too. This would actually cancel, and this would be the integral of x e to the 2x dx. So if you notice, we've run into a little bit of a hiccup here, because isn't this still multiplication of two functions? It's still a polynomial times an exponential. Remember, that's what you're trying to use this technique for. This technique is your go-to move when you have a product of two different types of functions. So we have an exponential, or I guess two different categories of functions. So we have an exponential function and we have a polynomial. So that means we have to do u sub again. So I'm going to do u equals, I'm going to do dv equals, I'm going to do du equals, I'm going to do v equals. So immediately I'm going to try the same thing as last time. I'm going to say that u equals the polynomial x. So then du would be dx. Then we're going to say dv equals e to the 2x, but you know, we've already done this problem. So we're going to know this one right off the top of our head. This is going to be e to the 2x once again. So now I can do a second u sub. Now this will become, I'm going to put brackets here to not forget to distribute that minus sign. This is where most people go wrong. So now the antiderivative of x e to the 2x is going to be u ultraviolet voodoo, so u times v, so this will be x, oops, I'll just write it out first, x times 1/2 e to the 2x, and remember, all I'm doing is u times v minus the integral of voodoo, v du, ultraviolet voodoo, so u times v minus the integral of v 1/2 e to the 2x du dx. And again, this is just a way to memorize it. If you guys don't want to use this technique and you just say, well, professor, I can just memorize it, well, fine, more power to you. So this is the integral of v du. That's all I'm doing. I'm just rewriting this formula that I showed you guys. This is what we're using every time, okay, for integration by parts. So this is a very plug and chug style of technique. It's not like this super, you know, you really have to think crazy about it. It's not sneaky. It's very straightforward. It's like, here's your attack plan, follow through with this, and it should work. Now, does it always work? Well, not in this case. Look, we had to do integration by parts twice. So just keep in mind, sometimes you will need to apply integration by parts multiple times. Okay, now the thing is, I just want you guys to understand there are other techniques that I've seen people teach. Some people use a table like this, and then they have you fill in the table. And that way you can do like, what if you need integration by parts 5 times? So the table basically allows you to do it. But what I've seen is, in that case, I've seen students know how to follow the table, but they don't actually know the integration by parts and what it's doing. They don't actually know where it came from up here, that it was just on a product rule. They just know how to fill in the table. So I don't really teach that technique. So the good news is that probably means I would never give you a problem that required more than 2 integration by parts on an exam. So integration by parts twice would be the worst I would ever do to you. You shouldn't need it 3 times or 4. But is there problems out there that exist? Absolutely. Okay. So let me just keep finishing this problem off. So now we have x squared over 2. You know what? Maybe I'll write it like this. Maybe you guys like this better. 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus, now we're going to have to integrate this guy again, and we're going to use that same u sub that we've already used twice. So this is going to become plus 1/4 e to the 2x plus c. Okay, and if we wanted, depending on how the book asks, they might ask you to factor out. So we could factor out a 1/2 e to the 2x, and what would that leave behind? Let's see here. That would leave behind x squared minus x plus 1/2 plus c. That's an alternate version of the answer. I could totally see the homework asking. I would accept this answer, absolutely. This to me is the correct answer, but you know, if they ask you to factor your final form, then you got to follow the directions. Okay, any questions about any of this, you can ask me in the meeting. Okay, so please, if you're having trouble with this, come to the meeting. Now I'd like to look at a problem involving integration by parts. Now with, what's it called? Limits of integration. Sorry, the name escaped me. Okay, so here's our technique for integration by parts with limits of integration. So we're going to do, oops, why do I keep writing backwards? U, V from A to B minus the integral from A to B of V du. Okay, so it's pretty much the same as what you know. I feel like the reason they want to separate this is sometimes you guys know you're going to have to do U sub on this one on the right, right? So this guy right here, sometimes you have to do U sub on. So that means you're probably going to sometimes change the integration, limits of integration. So they don't want you to confuse it with the limits of integration for over here. Okay. So this is our technique. So if I gave you this problem, the integral from 2 to 3 of ln of x dx. Okay. Now the thing is ln of x dx looks like an innocent problem. And in your mind, you're probably thinking you already know how to do this one. Most of you probably actually don't. It wasn't given to you in Calculus 1. However, this is a formula you can memorize. That's in the back of the book or in the integration tables. There is a formula to memorize for ln of x dx integrating. However, I want to show you where that formula came from. That formula came from integration by parts. So what we're going to do is we're going to declare our u and our dv. So according to integration by parts, LIATE, if we're working with LIATE, and again, LIATE is not some mathematical rule. It is just kind of a rule of thumb or a guideline that we use to try to decide what's U and what's DV. According to LIATE, which doesn't always work, I'd say it works like 90% of the time in my experience. Sometimes it is actually wrong. But LIATE says that logs are the first thing that you should make U. So I'm going to say that this is ln of x. So then that means du is equal to 1 over x. And dv then has to be dx, right? So then what's v? Well, v is just x, right? So now we have our integral of u times v, integral of u dv, sorry, my brain escaped me for a second there. So now we have to do u times v. So u times v would be ln of x times x minus the integral, and this is from 2 to 3, minus the integral of v du. So v du, oops, forgot the dx right there. V du would be x times du, which would be 1 over x dx, right, from 2 to 3. So when we clean this up, this will become x ln of x from 2 to 3 minus, now these actually cancel, which is nice, and they become 1s, right? So then this is just the integral of dx, but hopefully you guys know that one's pretty easy now. And this would just be minus x. So this is actually the formula you would see in the back of the book. So this is in the back of your book. Okay, so you might see that formula in the back of your book. Some people have asked me why we don't have an absolute value on this ln of x. Well, the reason is we didn't actually integrate. Notice right here, we never integrated ln of x. Right here, it's ln of x, and we differentiated. So we didn't get an integral. If it was over here, if it was our dv, maybe then we could talk about it. And even then, sometimes there might be ways around it. But yeah, in this case, we did not need the value of that. So now I just have to do 3 ln of 3 minus 3 minus f of b minus f of a. So this would be 2 ln of 2, right, minus 2. Okay, so this would be 3 ln of 3 minus 2 ln of 2, and then this would be minus 1. And that would be our final answer. There's not really much better we can do with that. So you guys may want to use your calculator, but if they ask you for the exact answer, this would be it. I think you might even see the computer. They might try to get fancy with it. So they might try to tell you this. They might ask you to put the powers back, and then notice it's subtraction. So then they could say, well, the natural log being subtracted is the same as dividing the arguments. So this would be 3 cubed divided by 2 squared minus 1. So then they might even try to get fancy and say, well, this is ln of 27 over 4 minus 1. So this answer and this answer are the same. There is no difference, but one is just manipulated. As you can see, the bottom one's cleaner. So if you see that in the homework, that would be the answer the homework wants. But I would be fine with this answer, 3 ln of 3 minus 2 ln of 2 minus 1, or a decimal approximation if they ask for it. Remember, do not use decimal approximations unless they ask for that, or unless you just don't know how to do it and you just want to get some kind of partial credit. Okay. Again, decimal approximations look like to me as a teacher that you're just using your calculator or something else to just hit enter, and you're not actually showing me you know how to integrate. So just keep that in mind as we're doing these problems. Okay, so let's look at another one. Okay, so the next one I have is kind of a really cool example. It would have more effect if we were in a classroom doing this, but that way you can it kind of is really important that you struggle with this to see what actually happens. So I'm going to leave it up to you to pause the video once we get to a certain point. Well, actually, you know what? Why don't you guys try to set this up? Why don't you right now try to do LIATE and decide what's U, what's V, and then do integration by parts and see where you get. Now, the thing is please pause the video now, do it, and then unpause the video in a few minutes, and I'll talk to you more about what to do from there. Okay, so you should have unpaused the video, and you should have declared your U to be your e to the x, and your du to be e to the x dx, right? And then we know that dv then has to be cosine x dx, and then we know that the integral of cosine of x would be sine x. Right, so we have everything we need for integration by parts. So we have the integral of, let's see here, e to the x cosine x dx. Now we've rewritten this in terms of u and v. So what we're going to say is this is going to be equal to u times v, so ultraviolet, so e to the x times sine x minus the integral of v du. Okay, let me put it like that so everybody knows. All right, so that kind of is a problem. And hopefully you guys see that as a problem, because look what we have. Don't we still have a trig function times an exponential? And if we go back and look at the original, we have a trig function times an exponential. So remember I told you from the beginning that the integration by parts, the goal or what you're hoping for is that the new integral that you create at the end is easier than the one you started with. Well, this isn't easier. This is the same. You just swapped out a cosine for a sine. Okay, so try to see if there's anything you can do, or let's just do integration by parts again. So pause it and let's do integration by parts again. Okay, so hopefully you guys are rewriting everything right here. So you have your u is equal to e to the x, so du is equal to e to the x dx, right? We have our dv is equal to sine x And then that means our v is equal to negative cosine x, right? Oops, sine x dx. So then that means it's worth that because the integral of sine x is negative cosine x. Okay, so now we have to rewrite all of this. So I'm going to rewrite the whole problem again. So if I rewrite the whole problem again, we're going to have the integral of e to the x, which is the original problem we're trying to solve for, right? So this was what I'm asked to evaluate. I shouldn't say solve, but evaluate. And then this is e to the x sine x minus, now we did integration by parts again, so we have to do uv, so this will be minus e to the x cosine x minus the integral of v du. So v, but v already has a minus, so then this is going to become a plus, right? So that would be cosine x e to the x, oops, e to the x v du, yeah, e to the x cosine x dx. So I used v and du, right? E to the x dx and negative cosine x. Okay, so I see another problem, right? We still have a problem here because this is still an integral of a exponential and a trig function. So I'm going to rewrite again. Let's see if we can make any headway. So let's see here, e to the x sine x plus e to the x cosine x minus integral e to the x cosine x dx, right? So I just distributed that minus sign. Okay, so then that'll become plus e to the x cosine x and then back to minus. So that plus sign has been flipping back and forth. Okay, and there's still a plus c that's going to float around at the end. We can't forget about that. So now we have more of a problem is, look at here. What are we going to have to do? Integration by parts a third time, but I have a feeling that it's not going to work because it's just going to keep recycling. It's just going to take its time and we'll end up back to where we started. However, what I'd like you to do is pause the video and see if you notice anything about this problem. See if there's anything you notice. Okay, so hopefully you guys noticed that this and this are identical. So what I can do is I can add the integral of e to the x cosine x dx over to the other side. So this is kind of sneaky, right? So this would become 0. And now we're going to be left with 2 integrals e to the x cosine x dx, right? They're like terms, so I can make them the same. So now I have the left side is the integral, and the right side no longer has integrals. All I have to do now is divide by 2. So now these cancel, and I'm left with the integral of e to the x cosine of x dx is equal to e to the x sine x plus e to the x, and you could factor this e to the x out if you wanted. It would be fine. All over 2 plus c. Now take a minute to look at that. That's kind of powerful. What we just did is we never actually found e to the x cosine x. We just manipulated the right side to have no more integrals on it, right? So we went way back here. Remember, this was the original problem. This was the original problem, right? Way back here, this is still the original problem. But notice the right-hand side does not have an integral anymore. So technically, we did evaluate the integral. So this is a pretty sneaky one. I think I have one of these when I put it in the homework. I think there is 1 or 2 of these in the homework. So just be on the lookout for that. And again, integration by parts, you'll start noticing like cycles are happening. You'll say, oh, wait, why am I doing that? Or why am I doing that? But overall, that should get you started. If you need more practice, I have a few more problems I'm going to do in the meetings. So we can talk about another problem in the meeting if you guys want. I'll go over some of these. But that'll do it for this video, guys, and I will see you in the next class.